confusion matrix. Confusion matrix, it's very important when we solve classification problems. So if you go to, if you want to make some changes, just to go to this example here in GitHub and try to plot the data in different way. When we are plotting it in x1 and x2, it will be look complex like this one, non-separable. When we plot it against x1 square against x2 square, it will be separable like this one. And then when it's separable, it's just very easy to solve, just using simple perceptron to get this decision boundary. So this is how we see the world around us. So when we change features, we will change. The problem will be different, but the solution will be the same. The accuracy will be the same. So now I want to start saying something about the confusion matrix, because confusion matrix is very important. Yes. So confusion matrix. Confusion matrix. It's a very, very important tool to perform evaluation of, or to describe the performance of any classifier. So, for example, if we have binary classification problems, for example, we have dogs and the cats. We know how many. We need to know how many cats are classified as cats, how many dogs are classified as dogs, how many cats are misclassified as dogs, how many dogs are misclassified as cats. So this confusion matrix, we can do it for binary classification problems. We can do it also for multi-class classification problems. And it's important because numbers which we can get from this confusion matrix are very, very important to describe the performance of our classifier. So when we look into this confusion matrix, it's just a matrix. We can talk about binary classification problems. It's 2 times 2 matrix or table. We have actual classes against the predicted classes. Actual classes, those are the grounded truth, right? So the actual classes, this is the reality, in fact, or the grounded truth. We have predicted classes. It is a machine prediction. So when you build a classifier, it will predict some classes. So the predictions from the machine or from the model, it will be predicted classes. In binary classification problems, maybe we have positive and negative classes, or +1, -1, or 0 and 1, for example. So we have something called the true positive. This true positive, it's the actual positive classes which are classified as positive. We call it true positive. False negative, it's the positive classes which are misclassified as negative. We call it false negative. So, for example, you have someone and he has coronavirus, for example, and he did this test and it's a false negative. False negative means he has corona, but based on the analysis and the stuff, the test, for example, he has been misclassified as negative. So we call it false negative. This one we call it type 2 error. Type 2 error, it's more dangerous, in fact, than type 1 error, because type 2 error, it's maybe someone has a disease, but he has been misclassified as negative. So this is a problem. False positive, it's a negative class misclassified as positive. So we call it false positive, because it's a negative, but it misclassified as positive. So we call it false positive, which is type 1 error. And of course, the true negative, this is okay. Someone is negative and he is being classified as negative. This is very good. So TB plus TN, it's accuracy divided by total, it's accuracy. So in this diagonal, in fact, in this diagonal, when we calculate true positive plus true negative and divide it by the total, it will be the accuracy. So true positive plus true negative divided by total. Maybe this total, it's equal n, for example. So we call it accuracy. This number is very, very important. Precision. Precision, it will be the total positive divided by true positive and false positive. So, this number, true positive divided by true positive plus false positive, we call it precision. True positive divided by true positive plus false negative, it's sensitivity. I guess it's sensitivity or recall. Yes. So, we will have the explanation here. So we have true positive. True positive, those are the cases in which we predict yes. So, for example, they have the disease and they don't have the disease, and they do have the disease. In fact, this is true positive. True negative, we predict no, and they don't have the disease, for example. So this is okay. True positive, true negative, this is no problem. False positive, we predict yes, but they don't have the disease. So it's type 1 error. False positive. So false positive, he is negative, right? So the ground truth here, it's negative. He does not have the disease, but he did some analysis and the blood analysis and stuff like this, and he has been misclassified as positive. So we call it false positive. He will take medication, but he doesn't need to take those medications, and hopefully those medications will not have a side impact on him, for example. But of course, if he is a patient, he will live under stress for a period of time, because he can just feel that he has, I mean, by numbers, he has coronavirus, for example, but he does not have. He does not have symptoms. Maybe he has another symptoms from cold or common cold. So we call it type 1 error. False negative, this is very dangerous. False negative, because he is positive, but he has been misclassified as negative. So we predict no, but they do have the disease. And we call this one type 2 error. We have prediction error. The prediction error, it's the sum of false predictions divided by the total number of predictions. False prediction. So if we can call here, we have here this accuracy. So if we can calculate this one true positive plus true negative, we can have here false negative plus false positive divided by total. It will be error, prediction error. So this prediction error here, this prediction error, it's false positive plus false negative divided by total, n, for example. Accuracy, it's 1 minus error. So the accuracy, it will be the sum of correct predictions divided by total number. So the accuracy here, it will be true positive plus true negative divided by n, for example, total. So those numbers are very important. We have precision, we have recall. So you need to get those numbers for any model. If you are working in classification problem, you need to get those numbers. Those numbers are very, very important. Maybe in the discussion part, you need to talk about those numbers, right? Type 1 error, type 2 error, and so on. We have here an example. It's an example. I used it in one exam before. So in total, we have 165, I guess 165, a sample of 165 data points. Those are the actual. So this is the ground truth. Those are the predictions by machine prediction, for example. So, for example, I mean, in this table, in fact, I give students numbers and I asked them to fill in numbers. I give them one number and I asked them to fill. So, for example, this is actual yes, and he's been predicted as yes. So, what is this number here? Can you tell me? This one, what is this number? Yes, predicted as yes.
True positive.
True positive. Okay. What about this number? He is actual yes and classified as no.
False negative.
False negative, because yes, false negative, because he is positive and he is classified as negative. Okay. What about this number?
True negative.
True negative. This is correct. True negative. What about this number?
False positive.
False positive. So we can get, I mean, if you have the table, you can get those numbers. True positive, true negative, false positive, false negative. And from those numbers, we can get other numbers as well. So we can find accuracy, for example. What would be the accuracy here? If we can go back here, what would be the accuracy? Accuracy will be true positive plus true negative divided by total, right? Accuracy will be true positive plus true negative divided by total. What will be true positive? 100 plus 50, 150 divided by 165, right? True positive. Sorry, accuracy. Can you find the accuracy? Irini, can you find the accuracy? I'm just, because not all people are using cameras.
Yeah, no problem. So accuracy, it would be true positive plus true negative. So 100 plus 50, 150.
Divided by
the whole n.
Okay, this is correct, which is 165, so it will be 91% accuracy. What will be the prediction error? One minus this number, right? So it will be 9%, correct? Or it's a false positive plus false negative divided by total. So false positive plus false negative, so it will be 15 divided by 165, correct? So this is an error. So I mean prediction error, it's 1 minus accuracy. So we just need to calculate one of those. We have something here very important, which is recall. A true positive rate. True positive rate, it will be total positive. It's when it is actually yes. How often does it predict yes? When it's yes, how many times we can predict yes? Right? So when I mean this recall, so it's yes. When it's yes, how many we can predict yes as yes? How many times? So it will be 100 divided by 105, because the total here it's 105. So we call this one its sensitivity or recall. So this recall is very, very important. We have also precision. What is precision? Precision, it's when it predicts yes, how often it is correct. Because in yeses here, how many yeses we can get, I mean the model is predicting, it's 100 times plus 10 times. But those 10 times are not correct. In fact, those false positive, right? This is false positive. So this one, it's a true positive. So in fact, the precision, it will be a true positive divided by true positive plus false positive. So here it will be 100 divided by 110. So it will be also 0.91 or 91%. So those numbers are very, very important. So whenever you are working in a classification problem, you need to draw, maybe I don't know if you really need to have the whole confusion matrix. Maybe it's not very important, but there are numbers which are important. You need to get accuracy. You need to get maybe accuracy or prediction error, for example. You need to get precision and recall, right? And there are other metrics which we can use, in fact. And this one, it works fine when the data set is balanced, but when the data set is not balanced, those numbers will not be correct. So this is very important. We need to, I mean, there are other things you need to look for it. So when your data set is balanced, we can just use this. When it's not balanced, we cannot use this. If we need to plot or to get the confusion matrix for a problem, I mean, when you train your model, we need to plot, or we need to get those numbers. How can we get those? How can we get the confusion matrix? We have a command here, in fact, called the confusion matrix. We have a command called the confusion matrix. Yes. Just use confusion matrix, and the input to the confusion matrix will be the ground truth and the predictions. Labels, actual labels, and predicted labels.
For disease, the best metric is recall, because it actually find how many of yes or how many of the positive positives are predicted, right?
Recall?
Yeah, for the disease recognition, which one of these metrics are better? I think it's recall.
I mean, recall, you can call it, it's a true positive rate. So in my data sets, in the ground truth, how many yes I have, and how many can you, yes. How many times you can predict, right? So
many people are sick, and the recall is the best metric because it actually shows that how many of the patients are, how many of the sick people are recognized.
Yes, this is correct. Yes, I mean, to get the confusion matrix, you can get the confusion matrix and you can get all those numbers, by the way. So you don't need to calculate those numbers. You can get those numbers directly from Python. So if you are using sklearn or Keras, for example, you will be able to get those numbers without any. You just need to write small lines in your code after training your model, so you can get all those numbers printed. Precision, recall, confusion matrix. So for confusion matrix, we have a command called the confusion matrix. The input to this function will be the ground truth and the predicted labels. So I have y and y predict. How can we get y predict? I mean, y predict, we will get it by predicting for test or for training. So you can have the confusion matrix for training, you can have the confusion matrix for testing, right? But of course, for training, maybe it's not very important. Maybe the most important it's for testing. So you will get the confusion matrix. We have also, I mean, we will come to some examples where we can print directly, we can get directly precision and recall from the code. Yes. I want to talk about back propagation, maybe, or MLP, for example. I want to talk about MLP. I mean, MLP, the basic unit here, it's a perceptron, right? So this one, in fact, in reality, it's a perceptron. So now we know a perceptron, so we know the building blocks of feed-forward neural network, right? So the main building block here, it's this unit. So we spend, in fact, maybe 3-4 weeks talking about this perceptron, but this perceptron is very important because multi-layer perceptron, it's called multi-layer perceptron or multi-layered perceptron. So the basic building block here is a perceptron, and it works in the same way, exactly, no difference. And I mean, this multi-layer perceptron, we just put it in this layer structure because it's much easier for calculation. I mean, weights here, it will be matrix. Weights here, it will be matrix. The outputs here, it will be one vector instead of number. So if I'm working with a single perceptron, the output here will be scalar. But if here, it will be just a vector. There is no big difference. So the output here from this layer, it will be a vector. I have here omega 1 and omega 2. So weights here are vector. So it will be omega x, for example, the decision boundary plus p. This one will be vector. This one will be vector. Here, x will be vector, as it is. And the weights here, it will be matrix, right? So the weights here, it will be matrix because it's in layers. So the weights here, for example, if I have n inputs, so omega will be maybe n times m. N number of inputs and m number of outputs of this layer. So, and of course, if you have several layers, it's the same. I mean, you can just put it in a for loop and make those calculations very quickly. So if you want to make very deep multi-layer perceptron, you can just put it in a for loop, for example, and just make those calculations very quickly when it's in matrix notations or when it is organized in layers. So in fact, they put it in layers because it's much easier for calculations. So if I want to get outputs here, how can I get outputs here from this layer? So the output here will be omega times x, correct? So if I want to get first numbers here, those numbers here, right? It will be omega x, correct? So it will be just omega times x. So I will get outputs here. And those outputs here, just fresh, I didn't apply those outputs to the activation function. So if you have, for example, Gaussian or whatever, so you need to send those numbers to the activation function to get outputs here, right? Maybe it's a Gaussian activation function, so you can just apply those numbers in one step. This one will be vector times omega times x. It will be net, for example. This net will be one vector. Just apply those numbers to the activation function. You will get numbers here. Once you have those numbers here, multiply those numbers with the new weights, which we can just call it CV, for example. You will get numbers here. Once you have numbers here, apply it to the activation function, you will get outputs, right? Once you have the outputs here, we have target values because those are output 1, 2, 3, for example, but we have the ground truth, we have labels T1, T2, T3, for example. So we need just to subtract. And then when we subtract, we will get the error. And once we have the error, we'll go backward adjusting weights as we did before in gradient descent. So feed-forward neural network, it's exactly the same as a perceptron, but instead of working with one unit, we will have multi-layered perceptron, right? We will have layers, bunch of those perceptrons arranged into layers.
Does this NLP have a bias also?
Yes, of course, it has bias. Yes, it's exactly the same. I mean, there is no difference. We have bias here, but maybe they didn't write it here because usually they prefer to put it as an input, right? So one of those inputs will be the bias. It will be +1, for example. We must have the bias. Bias is very important. It's a very important degree of freedom. And you need to know why bias is important. It's important because the decision line, because the bias, it will help me to just to have more freedom. I mean, when we if you have a decision line like this one, when we change omega, we change the slope, but when we have bias, which is y-intercept, we can change it, we can go up and down across y-axis. So it's a degree of freedom which is very important. Bias maybe is very important in to converge quickly, in fact, to converge faster. So bias, so we have here bias. So multi-layer perceptron, it's just multi-layered of multiple perceptrons arranged into layers.
Wait, can I ask one question then?
Yes.
So previously we only had one weight to account for, but now we have two weights in between the one layer. So the error that we get in the output, what weight do we use to update with that error? Because previously we didn't, yeah.
So for example, so we can take this example. This, I have some output here, and I have maybe a target value here, right? And we will calculate the error here, right? Johan, this is.
Yeah, I'm listening.
So this is your question?
Yeah.
I mean, this error, in fact, it came from all contributions from different layers and from different weights. So for example, if I have here weights or called, for example, V1, V2, V3, V4, for example. So those four are contributing to this amount of error, because those four are contributing to calculating the output here, Y. So Y here, in fact, it's function of V1, V2, V3, V4. And in the same way, the output here, I mean, V1 times the output here, for example, and the outputs here are coming from those calculations. So it has some responsibility coming from these layers, from those weights. So all weights are contributing, in fact, until we reach the input. So all those weights are in charge of the amount of error here. And that is why error backpropagation, when we adjust those weights, we will try to minimize this one by adjusting the weights here, and the weights here, and the weights here, and all places, right? So but maybe some weights have bigger responsibility. In fact, the weights which are connected directly to this one, maybe they have very clear and very obvious responsibility about this amount of error. So we will change those first, because they are closer to Y. So it will be easy to change those ones first, right? And after changing, we will calculate another error here, and this error here, it will be function also of those weights, and we will go from here to change weights here and so on until we reach the input.
But the error that you calculate at the second layer there, I mean, how do you compare it to a true? You don't know what. How do you know that error? What do you compare it to?
Yeah, this is correct. But in fact, we calculate it starting from the output, because we have something called it's a chain rule, right? So when we go backward, in fact, we start from here. We start from here using this rule, which called the chain rule. So we will go back from here, and we will calculate some errors here, and after that we will go backward and so on until we go to the input. But the problem,
couldn't you instead, like this, the one that you want to minimize here, the output function?
Mm-hmm.
So it could be a objective function that depends on all weights, and then you don't have to optimize them individually in each output layer, but with the whole net in mind, right?
So I mean, we calculate the error here. We need to define an objective function here, and you are right. We need to convert. I mean, this is just the error. This is the difference between this class, predicted class, and the output class, right?
Yeah.
So we need to define a cost function. So the cost function, we can just call it, for example, J equal maybe summation of maybe t minus y square, right? Divided by 2, like this one. Maybe will be the cost function which we need to minimize, right? So this cost function, it's function of y, in fact, and the y is function of those ones, and those ones are function of previous layers, and so on until we reach the input. So we go it step by step until we able to adjust all weights, because each weight here, in fact, has a kind of responsibility for the output here. So we need to change. We need to change all those. Maybe maybe one here does not have any responsibility. So maybe the rate of change here will be 0, but the rate of change here will be much bigger. Maybe, right? So it's about what kind of responsibility from each one. So I mean, creating this kind of error. So so I mean, in error backpropagation, we start from backward here and start adjusting weights which are connected directly to the output. And after adjusting those ones, we will adjust the weights of the second and the next layer and so on until we reach the input. So in fact, we start from backside until we reach front end or front side of the neural network. The problem here, sometimes this error will vanish quickly. And when we reach here, for example, maybe the rate of change here will be very, very small. You know, we calculate all-time delta omega, which is minus eta partial E by partial omega, for example, right? So as I told you, Johan, we use this equation all-time partial E by partial omega. If I want to change V, I need to calculate partial E by partial V. If I want to adjust to omega, I need to calculate partial E by partial omega, right? So I need to get this one, but I cannot come from here, from the back side to the front side directly. In fact, there is no direct connection. I need to go through my neural network because there is no outside connection. So there is no direct connection between this one and the output here. Maybe we can change it, the structure of the neural network, but in this form, which is in front of us now, there is no direct connection between the error to omega directly. So I need to go through V and maybe Z until we reach omega, for example. So we need to do it layer by layer until we reach the input. The problem, sometimes partial E by partial omega will be very, very small number. When it's a very small number, delta omega will be 0. And when delta omega will be 0, we will not be able to adjust the weights which are connected to the input layer, for example. And this is a problem because when we start the neural network, we initialize all weights by random values. So just imagine that we initialized all those weights by random values. And in the training process, when we try to adjust those weights, delta omega is very, very small. It's close to 0. So in this case, we will keep those random values as they are, which means that what this layer C will be those weights multiplied by inputs. So my inputs, maybe it's an image, maybe it's text, maybe it's time series. Now I'm multiplying it by random values. So random values time in number, it will be random values. So this is very, very, very challenging, in fact. So vanishing gradient, it's a problem. So vanishing gradient, when this rate of a change will be very, very small, and we will not be able to adjust weights connected to some layers. So the input to this one will be just random values. So in fact, we are destroying, in this case, we are destroying our images. You have an image for a person, but you multiply each pixel value by a random value. So you have pixel value multiplied by random value, so it will be just random, right? So so maybe if the problem is working, we will have really big problem. So we need to be able to discover if we have this kind. So it's recommended, in fact, to not go too deeply. In fact, don't be too deeply. So don't select multi-layer perceptron with many hidden layers, because it will be too deep, and then when it's too deep, maybe some layers will not be able to be trained, right? So so don't try to go deeply when we are using multi-layer perceptron, and maybe also try to use different activation function, because last time we said that there are some activation functions which is squash, and then when we differentiate those functions also, the first derivative will be very, very small value. When we use the chain rule here, we will have several multiplications. Several multiplications of small values will be much smaller values. So we need to avoid using those activation functions. So we need to use activation function which has better performance with vanishing gradient. Yeah. So how backpropagation work? So we start from the output layer. We calculate the error. We get the error. We calculate the objective function, which will be half, for example, summation t minus y square. And if I want to adjust, for example, those weights here, v, for example, so I just simple. I mean, I need to calculate delta v, which will be minus eta partial e by partial v. I just need to calculate this one, right? There is no direct connection between the output here and the v. So I need to find the first partial e by partial y. So first, because there is direct connection, I mean, e is function of y, right? So first I will find partial E by partial Y, and after that I need to get partial Y by partial net, and after that net will be V times the output here. So I need to get partial net by partial V. So now I have partial net by partial V. So partial E by partial V, it will be this number. So I need to calculate those values. So partial E by partial V, we will calculate it using this chain rule, right? Once we have this one, we will calculate delta V. So now I need to adjust those weights. So HV will be V plus delta V, for example, and we'll adjust those weights here. Again, if I want to go to this layer, for example, imagine this one is omega, for example, I need to adjust it. We will do the same, right? So I need to get delta omega, which will be minus eta multiplied by partial E by partial omega. How can we get partial E by partial omega? Is there any direct connection between E and omega? No, there is no direct connection. So in this case, I need to use also the chain rule. So partial E by partial omega, it should be, for example, partial E. It will be the same. I mean, we will have some more steps here. I have the derivation, in fact, so we can go to it. Maybe not today, but it will be the same. So I need to get partial E by partial omega. So I need to find the chain rule, which will help us to go from this layer to this layer. So I will calculate some error value here. We call it delta. So this delta, it will be maybe V, this weight value multiplied by partial E by partial V plus this one multiplied by this one, and I will use this one as the error here at that point, and we will repeat this process. But I have the details, derivation, and also implementation in details, in fact. Yes, how can we use MLB in sklearn? So just forget about error backpropagation. Maybe it's not very important, in fact, but we will have it at some point. We will discuss it in some point, and also we will have implementation of error backpropagation. But if you want to use MLB in sklearn very quickly, you just need to go to sklearn.neural network, right? From this one, we need to import MLB classifier. So MLB in sklearn, it's called MLB classifier. So so if I want to use it for confusion matrix, for example, we can get it from sklearn.metrics, this confusion matrix. So I need to use MLB for iris dataset because we solved iris dataset in the last slides using as multi-class classification using a perceptron. Now I need to solve it using MLB. So just try to use MLB classifier, import confusion matrix, load your datasets, divide your data into training and testing using this command, right? Right. So just for this one, for hold out validation. So the test set equal 0.2, which means the training set equal 0.8. So the data has been divided into 80% for training, 20% for testing. And after that, this is your classifier. You need to select a solver, right? So this is, you can just call it model equal MLB classifier. You need to select those numbers inside. So for example, we need to select the classifier which will be used for training. We'll call it the optimizer. The solver here, it's optimizer, and the SGD, it's stochastic gradient descent. We need to maybe select this random state to initialize your weights, right? Because when we build a model, we need to initialize the weights with random values. We use this random state, random seed, in order to to reproduce the results one more time. So when you specify this one, in fact, each time you will get the same model with the same initial values. This is very important. The hidden layer size, it's 5 units, 5 units in the hidden layer size, and we don't need to specify number of inputs or number of outputs, because number of inputs and the number of outputs, it will come automatically from the training data set. So this model, in fact, it will look like this one. We have only one hidden layer, and this hidden layer has 5 units. And how many outputs? In iris, how many outputs we have in iris? How many outputs, Irini? How many outputs?
I don't remember what.
In iris dataset, how many classes we have?
5? How many?
No?
3?
3, yes, 3 classes. So we will have 3 classes. And how many inputs?
4 input.
4. So we have 4 inputs. So it will be like this one. So this is our MLB. So it will be just like connected like this one.
The solver, do we have batch gradient or just a stochastic gradient?
No, just it's just I used the stochastic gradient descent, in fact. So I didn't specify any batch size here. So it's stochastic gradient descent, right?
So yeah, I want to know that the solver, the MLP classifier function, does it have built-in function for a batch gradient or the other gradient methods that we use?
No, I mean this optimizer, it's different about the training mode. I mean the other one, it's the training mode, right?
Right.
So this is the training mode. I'm not talking about the training mode. It's yes. So it will be the model will be like this one. So this is MLP, which has only one hidden layer, right?
It's different than the stochastic gradient that we have talked about in the last session.
Because in batch gradient, you need to specify the batch size. For example, you need to select, is it batch gradient or is it mini batch gradient? So please check MLP classifier and check by default. I mean default numbers. What are the default numbers? I'm not sure, in fact, if it is batch gradient or stochastic gradient. Maybe someone can check it. Please just write in MLP classifier, so you can check how it is trained. Is it batch gradient or it is MLP classifier? So I mean, if we check here numbers, the solver, we can select SGD add-on. There are many solvers.
There
Batch
also
size, yeah, the batch size, it's a minimum size of many batches of stochastic. It's a default is automatic, in fact, and when it's automatic, will not use mini batch. Some solvers don't use mini batches, and the batch size will be minimum between 200 and the number of samples. So, for example, here in this problem, we have how many samples? We selected 80% of 150 as the training set. So so it will be 0.8. I mean, the sample size will be 0.8 times 150. So it will be 120, correct? 120 data points. So so the batch size here will be 120. I mean, because when you select it, you can select the batch size, right? You can select the batch size. If you didn't select the batch size, but it's a trend in batch size, in fact. So it's a batch learning. So this function will work in batch learning, but because here we didn't specify the batch size, so it will be automatically selected as a minimum between 200 and number of samples. So it will be 120. So it's batch learning. So it's a batch, it's not stochastic. So it will not train example by example. It's not online learning, but it will be batch learning. Yes. So so this is the multi-layer perceptron. We have one hidden layer. This hidden layer has 5 units. Output layer has 3 units because we have 3 classes. This is the number of classes, right? And this is the number of inputs. We have 4 inputs. And we divided the data into training and testing. So we will use X-train, Y-train for training our model. And after that, we will get the predictions. And for the X test, so I get the predictions for the X test. You can calculate predictions. And after that, you can plot your confusion matrix. The confusion matrix, it's for Y test and Y predict. Y test, and because I'm doing this confusion matrix for the test set, so we need to compare between the ground truth of the test set and the predictions. And if you can see it, I have it here for training and testing, in fact. and for testing, I mean the accuracy it's 100%. So we have 3 classes. So class 0, we have 10 from class. I mean the data point is 20% for testing and 80% for training. I mean, so 100 data point, 120 for training, and the 30 points for testing. Those 30 points, 10 from each class. So here in the test confusion matrix, we have 10 from class 0 classified as 0, 10 from class 1 classified as 1, 10 from class 2 classified as 2. So the accuracy here, in fact, it's 100%. Right? This one, it's for the training, and in the training we have 120 examples, 40 from each class. So 40 from class 0 classified as 0, so the accuracy for class 0 is 100%. 37 from class 1 classified as 1, and the 3 from class 1 misclassified as 2. Right? So we have here a problem. And finally, from class 3, we have 40 from class 2 classified as 2. So maybe the accuracy here will be like maybe 70, 97% or something for the training, but it's 100% for testing. Yes. So now if you have a project, you can start working with MLP, multi-layer perceptron. So in multi-layer perceptron, you just need to specify number of hidden layers. If you want to use 2 hidden layers, how can we do it? You just need to change this one into 2 values. Maybe 2 hidden layers. The first one has 10 neurons and the second one has 5. It will be like this one. So you just need to specify number of hidden layers. And you need to select the solver or the optimizer. Maximum number of iterations. I mean, you just go to sklearn and try to find all default values. Even in the activation function, we can select different activation function. So for example, I can select RELU, for example. So if you want to select RELU here, you can select RELU and check the performance. So I can try to change it to RELU and
sorry, while you're looking, this is the second example where we had that the test accuracy is higher than the training accuracy, or the accuracy applied later of the model applied later on a training data set. Is this common, or is it just
in the test set?
Yeah.
No, it's not. In fact, by logically, it should be less, right?
Yeah. So maybe it's because it's just Iris is very simple data set. Yeah.
Yes. Yeah. Maybe I mean the data set is simple, and yeah, maybe the model is maybe more powerful. For example, but it's very close. I mean, this one it's maybe 98% or something, just 100%. But I mean, of course, for the test set, maybe I don't know. In fact, but it should be logically, it should be less than the training, right? So the accuracy here should be better than the test. So so maybe we have some. So I mean, you can select. If I can show you here, I can stop sharing my slides. I can share something else.
Can we use MLP for image noise reduction?
Multi-layer perceptron for image what?
Noise reduction, reducing the noise of the image.
Yeah, why not? Why not? Like in autoencoder, for example.
So what is the input and output of this?
The input will be image. The output will be image, right? And
right.
But in this case, you need to use autoencoder, right? Because I want to use it for image reconstruction or image noise reduction. So, but I mean the autoencoder, it's a feed-forward neural network, in fact. So it's the same type of this one, feed-forward neural network. A number of inputs should be the number of outputs, but it consists of 2 parts, one called encoder, one called the decoder. The input will be the image plus noise, the output will be the clean image. And I will train it to reconstruct the image without noise, or to remove the noise. Right? So it's autoencoder. We will talk about autoencoder also maybe today or next week. Because autoencoder, we can use it for dimensionality reduction, and we can use it also for noise reduction, or removing noise from images. So if you can see my slides here, if you can go to this one, so you can select activation function. I mean, you can just select logistics, identity, hyperbolic tangent, RELU, in fact. So, but by default, by default here we use ReLU. So in my example here, I didn't use any activation function. I didn't select activation function. So it's by default, it's ReLU, but you can select between different activation functions. I mean, also the hidden layers. By default, you have one hidden layer, which consists of 100 neurons, for example. So if you didn't specify number of hidden layers and the number of units in each hidden layer, it will be only one hidden layer with 100 neurons. Those are the solvers. We have this LBFGS, and we have this SGD. We have Adam optimizer. Adam optimizer, it's a stochastic gradient-based optimizer. SGD, it's a stochastic gradient descent. We have alpha, we have batch size. I mean, the batch size also, if we didn't select it, it will be auto. And when it's auto, the batch size will be minimum between 200 and the number of samples. So learning rate, it could be constant. It could be inverse scaling. And it could be also adaptive. So by default, it's constant. Learning rate and all those numbers. So in fact, there are many learning rate initial, for example. So there are maximum number of iterations. If you didn't select it, it will be by default 200. Shuffle, if you want to shuffle in each iteration, for example. So it's only used when you are using solver SCGD or Adam. Random state for initialization. This one verbose to plot or to print outputs from the training. Momentum term, for example, and so early stopping, if you want to use early stopping. Validation fraction. So you can, for example, if you want to use, by default, it's 10% validation fraction. So if we need to use here validation, so we can just use validation fraction by, it's by default already 10%. So we have validation fraction. By default, it's 10% or 0.01. You can just change it, maybe 0.2, for example, right? So it could be something like this one. So there are many things. I mean, you need to go back to, I mean, those documentations and try to, I mean, change those hyperparameters and play with those numbers. Yes. Because time is running, so I will go back to the slides. So this is the confusion matrix of the model, right? If you want to use it also, I mean, we used it now here for this iris dataset. If you want to use it for MNIST, MLB for MNIST. MNIST, this is a dataset. It's 60,000 examples for training and 10,000 for testing. So it's already divided. You don't need to divide it, in fact, because it will be already, when you download those datasets, when you import it, you will get 60,000 for training and 10,000 images for testing. And each digit consists of 28 times 28 pixels. So in fact, each digit is in 28 times 28 pixel values, right? So it will be like this one. And people just writing, for example, 5, it will be like this one. Yeah, it's like this one. And it's normalized. Its digit has been normalized and centered in a fixed size image. It is good database for people who want to try learning techniques and pattern recognition methods and so on. So I mean, this MNIST is very, very important also data set. So if we need to use MLB classifier for MNIST, how many inputs here? Yes, please, can you try to answer if we need to use, I mean, this MNIST data set, we have 10 classes. We have 10 classes, which we need to classify. We have from 0, 1, 2 until 9. We have 10 classes. How many inputs? How many inputs here? So each input will be an image. And the size of the image will be 28 times 28. So how many inputs?
Pixels in each image. The number of pixels in each image is the...
Yes, it's a 28 times 28. This is correct. So in fact, if I want to build MLB for this problem, you just need to select number of hidden units, number of hidden layers, right? And number of outputs. Number of outputs will be 10. Number of inputs will be 28 times 28. So number of inputs will be 28 times 28. Connect. Maybe you need to use 2 hidden layers or 3 hidden layers. number of units, you can just select it, right? And the number of outputs will be 10 because we have 10 classes. If we need to, yes, just I used MLB classifier from sklearn.neural network. I used the MLB classifier, and at the same way also I used a confusion matrix from sklearn metrics, and we have a very nice function called the plot confusion matrix. It can help you to plot the confusion matrix. And from data sets I got MNIST. So this is a data set. In fact, we got it from keras.datasets. You have this one in Keras. You don't need to download it from anywhere. So you just need to get it from keras.datasets, this one. We have very nice function because the data set here, I mean the labels here, it's just 0, 1, 2, 3, 4, 5, 6, 9. We cannot accept it. In fact, we need to convert it into one-hot encoding. So we have function called the toCategorial. This function will convert those classes into one-hot encoding. So the classes, remember the classes, we have 10 classes, one class called 0, one class. So we have images. Maybe this image will be 0, another image will be 1, another image will be 9, another image will be 7. So in fact, labels here are categorical. We cannot accept it. So we need to convert those numbers into one-hot encoding, So in one-hot encoding, how many classes we have? We have 10 classes, right? We have 10 classes. So you can just use, you can put each class into a vector like this one. For example, if when it's 0, it will be, it will be 1 here and the zeros elsewhere. So this is 0, 1, 2, 3, 4, 9. It will be like this one. So each 0 label will be converted into this one. Each 1 will be converted into this one. When it's 9, for example, it will be converted into 1, 0, 0, zeros. At the end here, we have 1. So it will be like this one. We call it one-hot encoding. When it's one-hot encoding, we are sure that the output is 1 when it belongs to the class, right? So it means we can just use the output as probability, in fact. So for example, if you have an image which is 9, we need to see what will be the probability that this one is 9. So we will have 10 outputs. So maybe one output is 0, one output is 1%. Maybe 9 is confusing with 7 and 8. Correct? We can be confused between 7 and 8 and 9 and 8. Because some people just write 9 like this one, it looks like 8, looks like maybe 7, right? So sometimes we have some kind of confusion. So when we use one-hot encoding, the output should be 1 when it belongs to this class or number close to 1. It's a probability. So anyway, we will use this function toCategorial, and this function will help us to convert all those labels into one-hot encoding. So first, we need to get the data. So the data is already divided, right? So X train, Y train, and X test, Y test. And as we said in the last slide, we have 60,000 images for training and 10,000 for testing. So we will get it directly using this one. So now we have our images. After that, you can just plot it. If you want to plot some images, you can just plot it. And I need now to define my model. So this is my model MLB classifier. I will use this one. I will select this solver. The activation function this time, I want to use logistic. So I will use logistic. You can use ReLU. It's up to you to select. The number of hidden layers, we will have 2 hidden layers. The first hidden layer will have 100 units or 100 neurons. The second hidden layer will have 30. You don't need to specify inputs and outputs because inputs and outputs, we will get it from the training dataset, from this one. So if I want to plot this example, it will be 2 hidden layers. The first hidden layer, it will be 100 units. The second hidden layer will be 30. So this one will be 1 to 30. This one will be 1 to 100. We have 10 outputs, 1, 2, until 9, maybe starting by 0, 1 until 9. And we have here inputs. We have very lots of inputs, pixel values. So it's 1, 2 until 28 times 28 pixel values. So this one will be my feed-forward neural network for classify MNIST dataset. And after that, we will train the model. We trained the model. If you want to get the score, training set and testing set score, you have this function. It's called mlb.score. From mlb, you can get training score and you can get training and testing score. For example, you can predict using for the test set. When the input is test set, you can get prediction for the test set. You can use this one for calculating the confusion matrix. I mean, the input to the confusion matrix will be the ground truth, which is y test and y predict, this one. And after that, plot confusion matrix. So it will be like this one for training, this one for testing. As you can see here, Mattia. So now here it's for the training, it's more logical. For the training, the accuracy 99.31. Yeah. For the testing, it's 94.5 or 0.8. And this is the confusion matrix for training and for testing. If we can look into it, for example, we can look into class 0, for example. We have 974 correctly classified as 0. We have some points classified as 2. So some zeros classified as 2, some zeros classified as 3, some zeros classified as 6, some zeros classified as 8. And this is normal, right? Sometimes you get envelope or post, for example, people are writing there, and it's hard to read it, in fact. So sometimes we get confused, and if we can get confused, the machine also should be get confused. So maybe we have some problems here, some more problems here, if you can see it here. And it's confusion between 8, 9, and maybe 3 and 4, right? So, and it could be logic. Maybe 8 and 4, sometimes they are confusing. Maybe 9, 3, 4, maybe. So we have some confusion here. It's some more confusion. We have here a problem also. Do you see this one? So in fact, it's confusion between 5 and the 3. This one.
What is the first column? It's like, what are those all numbers in the first column?
What?
The first column. And what are those numbers? It's like 8.
Is this true? True.
Yeah.
True. It's a ground truth, right?
Right.
And this is a predicted.
No, the first column under 0 for the test value, it's predicted labels. There are some values like 8, 35, 21. What are those?
Those numbers?
Yeah.
Yeah, those numbers are confused as well. So it's 2 confused with 0, in fact. So 35 images of 2 confused with 0. This one 24 from 4 confused with 0. 32 from 5 confused with 0. I mean, 0 is the problem really, because many letters many characters can be confused with 0, for example. So 5, it's logic that 5 can be confused with 0. 6 can be confused with 0. 8, 9. So we have big problem here. In fact, lots of confusion between 0 and all other digits. This one, right? Because it's a 0, and because 0 like this one, 2 like this one, maybe can be confused. 3, maybe 4 can be confused. So sometimes people, when they are writing very quickly, maybe it can be confused with other. So we have big confusion, in fact, between all digits and zeros, this first column, in fact. So we have here a problem. So maybe based on this information, you can build a system for 0 only, right? Maybe 0 against the rest, maybe, if you want to improve the accuracy, because we can see that we have big confusion between 0 and the rest of numbers. It's the same problem here as well. So maybe we can take 0 outside the group, for example, and try to classify it by itself, build a model for it, for example. So yes. Yeah, should we take a small break and go back? Or do you want to take one, maybe 5 minutes break or 6 minutes as well?
Yeah, maybe yes, just to get some coffee.
Okay. Yeah, so we can just get some coffee. Thank you very much.
I posted something on the chat that I found yesterday. It's from TensorFlow. We haven't used it, I think, yet, but it's like a